Hi, I'm Gal. I'm a physicist and did my PhD in cold Rydberg atoms and have been working at a company called Quantum Machines for about 2 years now. Today I want to tell you about a set of tools we've been working for a few months and I believe can improve the workflow in many labs, especially in ones that run quantum experiments. First, let me say something about quantum machines. We're building the quantum orchestration platform. It's a hardware and software platform which provides a way to easily and intuitively control complex quantum experiments. At the heart of our solution is a chip architecture designed specifically for quantum experiments. It enables generating RF and microwave pulses in a fully parametric way, meaning pulses are synthesized on the fly, acquire and manipulate input pulses, perform arbitrary classical computation at real time, and there's a rich mathematical library, including everything from arithmetic through trigonometry and other mathematical functions, and even neural network activation functions. And complex control flow for things like conditionals, for loops, while loops, switch statements, and more. And all these are built to scale over many qubits. Everything is controlled from our programming language, QUAM, which is compiled for the pulse processor by our compiler. Okay, so now let's speak about a typical lab workflow. It would be great to think about it going in some linear fashion, starting at a measurement, recording the data in some way, crunching the numbers, doing some follow-up measurements, and finally publishing. Sadly, in reality, things look a lot more like this. There are usually many calibration steps needed before you can do a real measurement. You need to be able to record, update, recall parameters you determined by the calibration steps and use them accordingly. You need to perform data processing in between parts of the process. Recalibration needs to be done periodically, or when a measurement indicates something is not functioning correctly. Inevitably, everything breaks, and breaks often. Because it's inevitable, error recovery must be integral to the process. There are also things that don't feature on this diagram. A big one is programmatic one. Debugging your code needs to be simple and intuitive, and it is in fact part of the whole process. Another is version management, and there are many other problems. For example, finally, there is a big problem in observability. You can't put out lab fires if you can't see them, and you need the system to help you to find those fires. In short, there are many non-trivial tasks, and building a system to run an experiment, thinking about these features must be factored in. Entropy is a project to tackle these challenges and others around lab workflow management. It's a growing project, but there's already enough there to only allow me to scratch the surface in this talk. Nevertheless, I want to show you some of the things we have already implemented. If you want to try it yourself, you can check out the Python package on the PyPy package repository, view the project code and progress on the Entropy repository on GitHub, and of course visit us later at the QUAM booth. So how do we tackle some of the problems I mentioned before? Well, the first thing you need to do is to select the right tools for the job. The world of software engineering has advanced tooling and methodologies in place for practically every step in the development, testing, and deployment phases. There is lack of the right tooling in a lab because adopting advanced tools can have other overheads that we as physicists are not keen to pay. We want to put such tooling in the hands of experimentalists. The Entropy Lab package deals with the overhead needed in setting up some of the tools I mentioned before. A backend for data persistence and persistence of instruments is provided. This is implemented such that you can use either a simple single file database or a full-fledged one. Either way, you get the functionality of a SQL database. More crucially, this means you can query your data in complex ways, like getting a specific parameter from all the measurements done in a specific time by a specific user. And this is much better than my old archiving method in the lab, which was having really long file names with as much information as possible and just hope for the best. Secondly, we include a way to author complex experiments by describing them as multiple nodes connected on a graph, such that they are connected nicely and communicate. And I'll show a small example of this in the next slide. Breaking up an experiment into modules is nice. It's encapsulation, which makes reuse of components easily doable. This is highly relevant, especially for things like calibration. Encapsulation is good programming practice, and it's a good practice for the lab as well. On top of that, we make sure data, meaning results and metadata, is collected automatically by the nodes for you and saved to persistent store. Finally, Entropy Lab provides a graphical interface from which you can sift through results, querying for experiments where the planets aligned, and things made the most sense. I'll flash a picture of what this looks like in a couple of slides. This is a fairly typical and highly simplified calibration to experiment flow involving a few qubits in a superconducting qubit experiment. The different calibration steps feed each other en route to some target algorithm. This image was automatically generated by the Entropy lab code that was written to describe it, and this was achieved in just a few lines. We first generate the resources that will be consumed by the experiment. These are saved to persistent storage in the SQL database. Drivers for instruments go here as well, for example. And the database itself is a resource. Each node has a payload program which it runs when it is ready. Its results can then be passed to other nodes. Each node is an object, and by pointing the input of one node at the output of another, data is piped through. You then generate the experiment graph by passing a list of nodes to be used when constructing this object. The nice thing is, whatever resources are contained in this lab resources object, it's automatically available to any node in the graph. You don't need to explicitly pass anything. Managing your data is best done with a graphical interface. I don't think everything is best done graphically, but this side of things definitely is. When things are done graphically, we believe it's much better to use web technologies for building the interface. This automatically gives you the ability to interact with your lab remotely, which is always nice and sometimes necessary. I don't want to cover this in too much depth, but this screenshot should give you a feel. There's a list of experiments which can be filtered, plots can be manually or automatically generated, and there are some other nice features hiding here too. I invite you to check them out yourself. We've discussed the importance of encapsulation before. That's an important and useful principle in writing software in general and experiments in particular. Another principle which can be taken from the world of software design is abstraction. It's important to form the right mental model to free our mind to think of in the simplest useful terms. The model we include as part of this package is the Quantum Abstract Machine, or QUAM for short. It creates three different personas: the builder of the lab, who is the person who knows everything about the lab and connects and how things are connected, the user, who's the person who's running the experiments day to day, and the oracle, which is a service which allows to query the system and see what it can do. It's useful for connecting things to a higher level in the stack, for example, for a higher level programming language compiler. This is a small snippet showing how the admin can easily set up a lab. The admins add instruments to the lab, but the user doesn't have to think in terms of voltages, currents, and channel numbers if they don't want to. The abstraction by which the admin wants users to think of the lab is then set up. In this case, they are flux-tunable transmons. Any setup or configuration that needs to be done for this abstraction to exist is done automatically, and persistence is also automatically taken care of. QUAM provides a way for users to parametrically describe a lab, as you can see here. These parameters can be numbers, but they can also be set by calling functions, which allows to transparently bind the abstraction layer to any devices in the lab. As a user, things that were set up by the administrator are just available for you. For example, any parameter that was set up by the administrator is now available for the user. The administrator and user have a fully shared state, but have different views into the system. We took care of a lot of making sure that the autocomplete features of Python work here. So you don't need to know, as a user, what was put there by the administrator. You just hit the dot key on your keyboard and the options pop up before you. Here, for example, the user changes a flux line setting, thinking in units of megahertz. Don't take this example too seriously, but an instrument reacts behind the scenes. Finally, on this slide, all parameters are saved to a centralized parameter store, which is implemented such that you can easily move between states of the system. It's like a save game mechanism for your experiment, and it's quite convenient with features like named commits, reverts, and other nice things that you can check out for yourself. Okay, jumping quickly to one final key idea we bring forward with Entropy. It's changing of gears from things I mentioned up until now, and we believe it brings an important shift of paradigm in how experiments should be executed. I claimed before how running experiments as connected nodes, encapsulating your ideas, was a good thing, and it is. But now we claim that executing nodes sequentially, especially as experiments start to scale, is not the way to go. So why is sequential execution insufficient? So the thing is, experiments are distributed. Everything runs in parallel, and experiment nodes have a state. Experiments are event-driven, meaning data can arrive at any and all times, and reacting to events is needed. Experiments are in flow, meaning you cannot afford to slow down the execution of an experiment by just the executor itself. And centralized execution as a solution is a bottleneck that you must avoid. And finally, experiments are heterogeneous. There's different instruments, and they're connected over non-uniform channels like USB or GPIB or IP. And classical processing on many different targets is needed, and perhaps over a network. We've implemented a new type of executor that we think brings a paradigm shift to how this is done, and we call it Flame. Flame is an actor model distributed executor. It means things are event-based. Nodes react to things happening to other nodes. It's reactive and not a passive way of doing things. Nodes are processes. They interact like OS processes, and they can coexist. Nodes are processes, meaning that they can run arbitrary code, not just Python. They speak C, C++, LabVIEW, or anything else. Node communication is not centralized because, as I said before, centralized communications is a bottleneck. And node communication can run over any channel. You can run a process over a network. Now, because we're out of time, I invite you to see us at the booth to see how this type of execution works and how it can be used in your experiment.